Okay, here's section 3.4, and we are just looking at theorem 3.4.1. And so in this case, it says, suppose we have S equal subspace that we generate from the span of M vectors. Okay, and they say where at least one, one, well, I guess that's a one, at least one of x1 to xm is non-zero. Okay, so another thing we could just say is we could say xi is not equal to the zero vector for at least one I. Okay, well, and we could make that less than or equal to m, greater than or equal to 1, less than or equal to m. Okay, so we know now the reason they do that is, well, we could just have the zero vectors, in which case that's not very interesting. Okay, so if that's the case, then S has a basis formed by some of the xi's there. Okay, now it could be all of them and so forth. Now the way they say it is, okay, if this is the case, so if we have S where it's generated by some set of vectors, at least one's not zero. If the others are zero, well, it seems like, well, why would you put them in? But it could happen. If you're constructing something else, you might end up constructing some zero vectors in there and essentially not actually know that you have those zero vectors. But anyway, if we know at least one is non-zero, then there's a basis in there somewhere, and the way they do it is S has a basis, and they use these xc1, xc2 up to some x cr, like that, where 1 is less than or equal to C1 is less than C2 is less than all the way up to CR, which is less than or equal to M. Okay, so all that's saying is that I can pick some of these vectors. Maybe it takes all of them, but I can pick some of those vectors out as a basis. And it's a pretty nice constructive proof. Okay, so we call this a constructive proof because if you were to do this with an actual set of vectors, you will construct the basis. And they call this the left to right left to right algorithm. Okay, and And so what we do is we let C1 be the I such that x sub I is the lowest indexed x sub j, I guess, that is not equal to the zero vector. Okay, most likely, if this is any decent sort of set, it's the first vector, but we don't know. I mean, we might have a zero in there. So you see, we're just lining these things up and saying x1, x2, x3, and we just go down the line, x4, m. And so we just start here, and we ask, is this equal to the zero vector? And if it is, then, well, forget that. And, we go here and say it's not equal to the zero vector. Then our C sub 1 is actually 2. Okay, it's x, so we get x sub 2. And that's our first vector. Okay, makes sense. Just go until we have the first non-zero vector. Now, they point out that if we had to go all the way to the end, so if our C1 is equal to m, then we're done. We have our basis, it's just xm. And so then that's it, right? Now the other possibility is that C1 was back to the left over here somewhere, and then we could check if x. Now I'm going to actually, well, yeah, if xk for k greater than c1. Okay, so for any vectors to the right up there, if that xk is a linear combination of the xc1. Now, I can write that as, so is a linear combination of xc1. Now, the only way it's a linear combination of xc1, so I could say instead is, well, let me just start with the if part. If x sub k equals a times xc1 for k greater than c1. Right, so, that would be a linear combination of xc1. It's just some constant times xc1. There's nothing to add to it because I only have the one vector. Then if that's the case for all of those up to m, right, so k less than or equal to m, if that's the case, then we're done, okay? We have our basis. It's x sub c1. Okay, because it's non-zero. It's certainly a linearly independent set. If I just have one non-zero vector, I can't make it 0 without making this A here 0. And so, and then here, if all the non-zero ones are just a multiple of x of c1, then it spans everything else. And so there you go. You've got your basis. And you march on this way, you know, okay, if not, then, take or let C2 equal some K. Let's see. Yeah, so they say, let me use a J here. Let C2 equal J, where J is bigger than C1. Okay, so I've moved to the right, so going back to my list here, you know, I'm moving to the right and just looking for the next vector. Okay, let's C2 equal J, J greater than C1, and J, the smallest index. So I don't want to move too far to the right. Smallest index such that x sub j is not equal to a x sub c1. And so now, you know, when I find this, right, I'll have two vectors, x sub c1 and x sub c2. And so again, my list of vectors, I've got x1, x2, x3, x4, x5, x6, x7, and so forth. Well, so what I did was, maybe that was the 0 vector. Might have been. Usually wouldn't be, but maybe it was. This one was x sub c1. Put my lines over those. And, but maybe this vector was just a multiple of x sub c1. Might have been. And, but this one's not. So now this is x sub c2. And so c2 is 4. Right? And we just keep marching this way until we get through all the vectors. And so continuing, what happens is that we're only choosing independent vectors, so we know the set's independent. So and we know that all vectors we didn't choose were in the span of the ones we did. Okay, so again, because otherwise we would have picked them. So this is a pretty neat proof, and like I say, it's a constructive proof. And so to get the span, all right, we could say xc1, xc2, xc3, all the way to our xcr. Okay, we know that that spans S. Okay, because it spans all our vectors that span S. Okay, so it spans S, and then B, they are independent independent by construction. right? We only took those that were independent. Okay, and they say, well, and we would call this the left to right basis. Well, yeah, I guess if I knew other stuff, you know. So, so they do an example. So let's go ahead and see their example. Example 3.4.2, and they say, you know, X and Y are elements of Rn and independent, linearly independent. Okay. Then they say that S equal 0, 2x, x minus y, and x plus y has a basis of 2x and minus y. Okay, so those two vectors. Well, so you see, as we go left to right, 0. So we have the 0 vector was the first spot. And so here's spot 1. And so we can't use that. And so our first non-zero vector is 2x. And that's in spot 2. So our C1 is equal to 2. Then we get to x, but x is just equal to 1/2 of 2x. So it's a linear combination of that 2x, so we don't want that one. Then minus y, well, I can't make minus y out of 2x because, oh, and that was position 3. So here's position 4. So, sure, negative x is another one. So my C2 equals 4. And then x plus y in position 5, I can make that. So x plus y is equal to 1/2, oops, not negative 1/2, 1/2 of 2x, my first vector, my C1 vector, and then plus negative 1 times negative y. And so that's not independent. And so there is my basis, 2x and minus y. Okay, so there's an example. An example, you know, another example. You know, I could have something in 3 space, like, okay, here is the vector 1, 1, 1. Here is the vector 1, 0, 1. Here's the vector 0, 1, 0. And yeah, we'll stop there. Okay, so this is my S. And so I look here, that's non-zero. Okay, so my first vector is, and notice here I'm not using the square braces, I'm using parentheses around this vertical matrix or vertical column vector. And it's just a little easier, and that's fine notation to do that. Okay, so our first one, well, it's non-zero, so that's our first one. Okay, so first is 1, 1, 1. Okay, now I go to the second one and I ask, is that a linear combination of the first? And no, it is not. 1, 0, 1 is not equal to some constant times 1, 1, 1. Because the only way I can get that 0 in there is if A is 0, and that doesn't do it. And then nothing else is going to work. So my second is 1, 0, 1. But then 0, 1, 0. Now I made it this way so I didn't have to do any matrix algebra to help me out here. That's 1 times 1, 1, 1 plus negative 1 times 1, 0, 1. Okay, so I didn't solve this as a matrix equation to find those non-trivial solution there. But yeah, what I see is that certainly I can make that. And so my basis for S, or a basis, okay, my left to right basis for S is those first two vectors. So the vector 1, 1, 1 and the vector 1, 0, 1. Okay? So there I found my basis for this set right here. Okay, and I just proceeded left to right, and for something bigger, what I would do is, I would start with that 1, 1, 1, and if I could do it by inspection like I did here, great. Most likely I can for the first two vectors. But after that, I might have to go to an augmented thing and look at the reduced row echelon form of the matrix 1, 1, 1, 1, 0, 1, and ... 0, 1, 0. And, and see that I have a consistent solution, right? I mean, what could happen here is I could get my reduced row echelon form, get an inconsistent solution, and if I got an inconsistent solution, then that would mean that vector is independent of those two. But if I can get a consistent solution, which I can, because all I have to do is subtract the third row from the first row, put it back in the third row, and I get 1, 1, 0, 1, 0, 1, and 0, 0, 0. Okay, that augmented matrix. And that one, I know I can get a solution because this part is non-singular, and so I can solve the 2 by 2 system that I have up there with those all being 0. Okay, so I know there's a solution, and that solution happens to be the 1 and the negative 1. And so I know that I can write 0, 1, 0 in terms of those other two vectors. Okay, so that's another example.